Hello, welcome to Science Rehashed. My name is Shan Ning.
Hello, my name is Mehdi Jorfi, and we are your hosts.
So we just started our account on Patreon. So if you'd like to support our mission, please go on and be one of our patrons. So today we have a Meet the Legend series, and it's our privilege to talk to a pioneer of synthetic biology and genetic engineering. He helped initiate the Human Genome and Personal Genome projects and contributed to nearly all next-generation DNA sequencing methods. He also co-founded 20 spin-out companies from his research.
He has a number of ambitious projects, like bringing back the extinct woolly mammoth. We are so excited to talk to Dr. George Church today. He's a professor at Harvard and MIT and leads synthetic biology at the Wyss Institute.
最前沿的科学研究
Science
Innovazione und Wissenschaft
Scienza
Достижения
كشف جديد
Scienza
一点不像
Pesquisa
Discovery. Rehashing Science. So, Dr. Church, can you tell us a little bit about your background?
I was born in Tampa, Florida, MacDill Air Force Base. Lived on the water, so got a lot of access to natural aquatic creatures. And so I was interested in almost all these aspects of it. And I decided that I was quite interested in almost everything that had to do with math and science. I didn't particularly want to specialize. So I was looking for something where you really needed all of them, and I found that in crystallography in my second year of college. And I did crystallography on a genetic material, which is transfer RNA, and that's what led me to genetics. I flunked out of graduate school in about a year and a half, and then I was a technician for a while, and then I managed to get into Harvard to actually do the real PhD.
Wow, so that's a very inspiring story. So currently I am a graduate student. I think it's quite inspiring to hear that even if you don't do well initially, that you can still make a huge impact later in life. So that's really good to hear, just because I think during the quals for a lot of my peers, they were quite worried about failing. And I was telling them, don't worry, I'm sure there's plenty of amazing scientists out there who, failed their quals the first time and went on to change the world. So, it's great that you are exact example.
What I did was beyond the second chance. I completely could not pursue graduate work at Duke because I had failed so miserably.
I kind of want to learn a little bit more about your initial research direction. So in undergrad, it seems like you're already focused on the research. So what were you interested in then? Has it evolved to what you're interested in now?
It was not very specialized, even though crystallography of transfer RNA sounds very specialized. My interest, I felt in order to do that properly, I had to master, math, physics, chemistry, biology, computer science, and to use them, pretty much all of them all day, every day. And I liked that. And also it involved automation. It was in 1973, this was like one of the few bits of automation anywhere in chemistry or biology. And I thought that the rest of the field needed some automation.
Speaking of automation, you aim for biological automation and also cost reduction of technologies and openness. Are these the main driving forces behind all your ideas? How do you recognize a problem and think of solving it through these lenses, most of which are way ahead of its time?
Well, that's very generous of you. I think it's maybe too easy to be ahead, and it's not particularly rewarding if you're too far ahead. It's like science fiction. But if you can, in my mind, I would connect the dots, and I would usually start with something where I felt that there was some societal benefit, some kind of technological benefit that might be factors of 10, because if you aim for a factor of 2, by the time you finish it, somebody else will have a factor of 3, and it was just a waste. But if you aim for several factors of 10, you either won't get there or you'll get there with a fairly easy margin. So I think one of the key things one of the key technical threads that goes through almost everything I've done that gave me, let's say, an unfair advantage was the concept of multiplexing. And a lot of people, molecular multiplexing is inspired by, but a little different from transmitting telecommunication signals, where you can multiplex through optical fibers or telegraph wires or various ways, where you'll mix signals in the same space and time. With molecular multiplexing, you can mix molecules, DNA, protein, cells that have been barcoded in some way. You can mix them and do a lot of processing that ordinarily would take, billions of tubes. You can do with one tube. And so basically it's or one fluidics device. The point is that you've got millions to billions of barcoded biological or chemical objects that then you can barcode at the beginning and then decode at the end. And that basically is very distinct from simple automation, where you say a human is pipetting in a million tubes. I'll have a robot pipetting in a million tubes. That basically consumes the same number of pipette tips, the same reagents, roughly the same time. A robot's not that much cheaper than a graduate student, sometimes more expensive. So it doesn't, that automation doesn't actually change the price unless you change something else. And the something else here is molecular multiplexing, where instead of a million tubes, you have one tube. Yeah, you can still do a million tubes, but each of those tubes is a million times more productive.
Can you give us a broad idea of the concepts or projects that your lab is currently pursuing?
Again, we kind of look at it from both directions, both forward from what kind of technologies we could add a factor of 10 to, and backwards from what society needs, and see if we can see a way to connect the dots. And so one of the things that's clear from our involvement in gene therapy, so that's one category of project, and that's much bigger than just gene editing. It's clear that that's expensive. And so what are the alternatives to it that bring the price of therapies in general down? One is avoiding therapies completely with genetic counseling. So that means dirt cheap, highly well-interpreted genomes available to everybody. And the other direction you can go is towards something that seems to be rare, seems to be complex, but is actually quite common and simple in some sense. And that is that many diseases, almost every way that you die in a wealthy industrialized nation, which thankfully or hopefully will be all of us soon. But anyway, 90% of us in a wealthy nation will die of things that don't kill 20-year-olds. And so aging affects everything, including like falling down. It increases the probability you'll fall down and the probability you'll die of that fall. But infectious diseases, connective tissue disease, so forth, brain diseases. So anyway, so we're working on aging reversal, not longevity. Longevity takes too long to get FDA approval, and we don't need to get the FDA to acknowledge aging as a disease. We just need to work on diseases that are high in aging. And if we solve one of those with something that happens to solve all of them, neither the FDA nor we need to worry about how many it's solving. As long as it does one, it will get approved. So aging is a big one. We're also working on immunology, virology, and neurobiology in various ways, applying synthetic biology to try to make better viral vectors, transplantable organs that aid the immune system, including things that more and more accurate brain components that are right now one of the harder things to transplant. And in a way, you could transplant every part of your body, but the brain is special in that since it has all the memories and fairly distributed, you need a very special way of doing cell therapies there.
Dr. Church has been finding very innovative solutions for many biological concerns. And so we asked him about a very well publicized and debated project of bringing back the extinct woolly mammoth.
So the mammoth, there as a child, like many children, I fantasized about large extinct animals and would build dioramas and so forth. And then fast forward to an inquiry from a journalist, Nicholas Wade, from the New York Times, who was covering the story that a little piece of mammoth DNA was being reported, sequenced, and he didn't think that was a big enough story. So he wanted to know, how would you check that you're if you read something and you speculate, oh, that's a mammoth gene that's different from an elephant gene, how would you check that? And you might do that by synthesizing a mammoth. And so he asked me if that was possible, because I was at the time, one of the few people who was relatively knowledgeable of both reading and writing, and had developed the technology, the next generation technology that was being used for reading and writing, or reading, and he felt synthetic biology. So that was the start, and I typically don't reject questions. I just do my best at answering them with that, and if they're speculative, then I clarify. And then I thought about it afterwards. And I said, we actually could do that, and I started doing it slowly. And it's been a back burner project. I mean, most of our projects have to do with human health, but it became a little bit more front burner when I started reading Sergei Zimov's works. He was an ecologist, environmentalist from Siberia. And I became quite inspired, and eventually started collaborating with Sergei and his son Nikita. And I think that's the main justification at this point. Once I saw a clear societal need for this, it became much easier to justify my own research. I mean, we are driven by pure science. We are driven by pure engineering. Not particularly applied engineering. But it helps if we have this societal pull, and that has to do with the need for herbivores that are bigger than all the herbivores were removed from many parts of the Arctic, Canada, United States, and Russia, and now they're being reintroduced in at least controlled, large controlled experiments. And the one that's really missing is the one that can knock down trees, which is an elephant family member. So we're really looking for cold-resistant elephants. We don't particularly care that we're getting the genes are from mammoths, but probably the mammoths have solved a complicated systems biology problem, and so we need to be respectful of the subset of genes that are relevant to cold resistance, so that we can preserve the 1,400 gigatons of carbon, methane that could be released, especially now that in the news is that parts of Siberia are over 100 degrees Fahrenheit now. If that stuff melts, there's over 100 times more carbon in the form of methane, which makes it effectively 3,000 times more global warming than our annual production right now. So imagine our current annual production, which we fuss over a few percentage changes in that, times 3,000.
Yeah, that's insane.
So I'm sure there are quite a lot of doubt surrounding this project. What keeps you motivated to continue projects like this?
Well, first of all, I'm very I encourage people to express doubts, partly because it helps me anticipate where the roadblocks will be, both technical and societal. But also, it's nice to get on record that it was hard, because very often what happens is they'll say kind of under their breath that this is impossible, and they'll block your grant and stuff like that. But there's no documentation of it. So then when you succeed later, they say, "Oh yeah, that was obvious. Not an achievement." So you want people to go on record as saying this is impossible or unuseful or expensive. So that's one part of it. And so you could say that I'm just delusional, that I think that everything is like that. So I've had the unfortunate history of having, 2 or 3 or 4 science fiction things turn into science fact under my watch, as part of my collaborations, let's say. And then that makes me think everything is like that. Everything is a factor of 10 million fold reduction in price in the future. And everything can be done in 6 years rather than 6 decades. So that's the delusional component. And it's hard to resist once if you had one breakthrough, then you can be modest and say, oh, that's never going to happen again. But if you have 4 of them, then you start to get immodest or superstitious or something. But the other aspect is part of the reason I can ignore critiques is because very often the critiques are much more superficial. So and they repeat themselves. So almost every time, I'm involved in some discussion about why something's impossible or a bad idea, I've heard all the arguments before, and I've thought them through and have incorporated them into my research program. So, for example, with the Mammoth, isn't it going to be lonely? Well, it's like, can't we make more than one of them? Can't they hang out with regular elephants? So after and then if you hear that again and again and again, you started getting confidence, either false confidence or earned confidence that that particular set of answers. Mm-hmm. And that applies to all the ideas. This is very different from science fiction. It might be inspired by science fiction, but science fiction, even so-called hard science fiction, which is based in science fact, they don't really connect the dots. They're quite happy to just say, then a miracle occurs in here, or just paint it with a very broad strokes. While I'm uncomfortable doing that, I feel I have to fill in the dots, at least hypothetically, and then work on reducing the price of each of those so I can see them happen within a short period of time.
So Dr. Church is one of the CRISPR technology pioneers, and this tool is currently a commonly used gene editing tool in labs all over the globe. However, there are some concerns when it comes to human gene editing, especially in embryos. So let's talk about those ethical, societal, and safety concerns regarding CRISPR technology.
Chinese scientists in November 2018 announced that the world's first gene-edited babies have been born with altered DNA to prevent them from contracting HIV by deleting a certain gene using CRISPR technique. The claim shocked scientists worldwide and raising questions about bioethics and putting a spotlight on China's oversight of scientific research. Recently, a Chinese court sentenced him for illegally carrying out the human embryo gene editing intended for reproduction for 3 years in prison. What I would like to hear, what was your reaction when you heard the news back in 2018? A number of things evolved over the last 2 years. What is your position right now?
Well, I was not surprised that someone did it, and I was not surprised that there was a negative reaction. I don't think that it was a public health crisis. I mean, it's not like this guy was Typhoid Mary or something, spreading disease without a license. It is true that he was convicted of practicing medicine without a license. But he did have he had quite a large staff working with him. So there were licensed physicians involved, as I understand it. So I think that was a technicality because there was justifiable international concern. I don't think that engineering the germline has a clear role yet. So in order, so part of the concern is that when the benefits are small, then the risks have to be very small. So that's part of the problem with GM foods is there probably are no negative consequences that have been documented, but the benefits perceived by wealthy customers are so small that they're just not willing to accept any risks whatsoever, even hypothetical ones. And I think the same thing applies to germline. So, because there are many ways to treat HIV. Now, some people misrepresented HIV as a solved problem. It is far from a solved problem. 2% of deaths are caused by HIV worldwide. So the fact that we can do this by quarantine or drugs or is not relevant if it's not working. But this is not a solution, because the places where it's not working are the poorest places, and this is one of the most expensive solutions. Gene therapy in general, not just germline. So it's at like $1 million. You can do gene therapy on T cells or hematopoietic stem cells for the same thing. So almost exactly the same treatment has been done on people who are infected by HIV. Again, expensive. Better approach to HIV is preventative. But if we broaden it to designer babies in general, again, most of what you want to achieve can be done by other methods like in vitro fertilization with prenatal genetic testing. Some of it can be done even earlier. If you don't like in vitro fertilization or termination of pregnancy, then you could do it earlier in dating. So I think that this is neither a public health threat, nor does it show much promise yet. That doesn't mean that one of those two things might change in the future. Anyway, I feel that it's a bit of a tempest in a teapot. People can justify getting upset about it, but to me, it's like having multiple international meetings with the top scientists so that we can ban jetpacks. Nobody's going to use jetpacks anyway. Personal jets on your back. I mean, it's ludicrous that is such an urgent public health threat that we need to have all the best minds working on it, working against it. So I think there's been an overreaction, and it underlies a kind of a exceptionalism we have, that if we do cosmetic surgery to, say, cure cleft palate, that's fundamentally different from changing the genes. Changing the genes with in vitro fertilization, PGD, is fundamentally different from changing them some other way, like CRISPR. So I think we need to we should be examining this from medical outcomes point of view, the equitable distribution, so that the costs are reasonable, rather than if it involves this particular molecular mechanism, then it's somehow more horrifying than another. I think we're using code, we're using shorthand, and we need to unpack it a little bit more. I'm very concerned about unequal access to all technologies. And so I study the few examples of technologies that are equitably distributed. Now, some are much better than they've ever been, like water and telecommunications. In principle, almost everybody has some kind of access to telecommunications. Maybe they'll borrow a cell phone from the next village over, at worst case. But it's still not equitably distributed. One of the few that is equitably distributed, is worthy of studying and repeating, is smallpox. That is something that is $0, 0 cents. No one ever has to spend any money on that over the last few years, not because the vaccine is super cheap or the drugs are super cheap or there's some surgery. It's extinct. Right. And so that was a beautiful public health strategy that I think was very cost effective. And we need to use that as inspiration for how we have it cost effective getting to a certain point, and then zero cost from that point on.
How does one develop a vision of advancing the field by a factor of 10, as you mentioned earlier?
And it's not just a factor of 10. It's sometimes, well, in the case of reading and writing DNA, it's 7 factors of 10. So it's 10 million fold over a fairly short period of time. And part of it is identifying fields that are ripe for exponential change, which typically, in the case of electronics, telecommunication, and reading and writing biological, biochemical components, what they have in common is the possibility of miniaturizing. And some of that miniaturization is done by the parallelization, say, of in microelectronics of having a mask and photons going through it. It's highly parallel. That's more than just parallel. And then processing all those in a multiplex in a bath. So the bath is treating the entire wafer simultaneously. Same thing is you can literally make wafers that do, let's say, the latest next-gen sequencing, and you can treat everything in that wafer simultaneously. So they're getting a shared experience, a shared reagent all at once, rather than doing them in separate tubes. So how do people in the future find factors of 10? It may be that we exhaust something, that's where we run out of Moore's law, or we run out of things you can multiplex that haven't already been multiplexed. I don't think that's true. I mean, a lot of innovators like to close the door after they've been through it and say, well, that's it. There's no more innovation to be done. But I think that's quite unlikely. I think there's plenty of innovation to do. And it could be the next generation. It won't be multiplexing or imaging. It'll be something else. But one key algorithm is to look for 2 new things and just put them together in your mind, whatever they are. It could be a new piece of biology, a new piece of technology from a non-biological field, and see if you can collide them in your mind. And the more of those collisions you make, and the longer you can keep it in your head before you reject it. So it's very easy. A lot of people have no ideas. Some people have ideas, but they reject them quickly. And the key thing is to keep colliding them and keep being somewhat open to the possibilities.
I love that. So you have been striving to bring the technologies developed in lab into the market to the consumers. And in that effort, you co-founded over 20 different application-based companies spanning from the fields of medical diagnostics, therapeutics, to genetic testing and editing, to synthetic biology and stem cell engineering, just to name a few. What advice would you give to scientists trying to follow this path of translating their technology and innovations and bring it to market?
Well, many of the things that scientists work on are not market ready. So I would say first advice is don't rush it. Don't jump prematurely. If it's very valuable to society, it will become painfully obvious to you soon. So many people will be bugging you that you realize that you won't get your work done doing your regular academic job if you satisfy all the requests. So that's a clear sign that it's time to spin it out. So that's one part of it. You can. So that's if you just got a research pathway, you decide whether it's useful or not. It doesn't have to be. Pure science is great. But if you want it to have a higher ratio of that sort of thing, then you have to be much more intentional about thinking about what society needs, not necessarily going incrementally towards it, but taking a jump towards it, which involves risk and so forth. So it's not for everybody.
So what would you consider to be the most revolutionary discovery or invention in the field of genomics so far?
Well, I think it's reading genomes more than writing them. If I had to make that initial bifurcation, you can't really write without reading and knowing what you need to change, and then you need to read it again to make sure you changed it. So reading is fundamental in that sense. I think also there are many expensive therapies that can be avoided by reading. You can now read your genome not for $3 billion, but $300, probably by the end of the year, $100, and once you get down to $100, it's basically free. You can the parts of society that save money can pay for it in the same way that parts of society that benefit can pay for Google Maps and Wikipedia and so forth. So, so it's more cost effective than most things that we do therapeutically with a gene therapy or synthetic biology. That could change, and then we intend for it to. But so the question, if you wanted to be more specific within the gene reading, I would say that it's fluorescent multiplexing, and that has the potential of going into fluorescent in situ methods, DNA, RNA, and protein in 3 dimensions, possibly 4 dimensions. But that some of that's in the future. But the past is clearly that we can now sequence almost anything, and we should be using it to sequence our entire what I call bioweather map, all the pathogens in our body and our environment all the time. It's so inexpensive. It's a fraction of the cost of the money we're spending on the current COVID crisis, which is probably $5 trillion or more. If we just spent a couple $billion sequencing our environmental and body pathogens, we could have avoided it, as well as many other diseases.
As we discussed, there are a number of crazy technologies and science that came out from your lab. What do you do to make this consistently possible?
Well, I mean, first of all, it's team effort, and I'm not alone. Never have been. In fact, I feel very uncomfortable whenever I publish a paper by myself. But so part of it is creating a culture, even initially a personal culture as I'm transitioning from graduate student to PI, but later a culture that involves everybody in the lab of failure is okay. Fail fast and do the more failures you can do, more likely you're going to get. I mean, I think there's an overemphasis when people talk about engineering. They make it sound like, oh, I just sat down with my computer-aided design software. I designed this thing, and there was no trial and error. There's a ton of trial and error, and you should embrace that in your own personal life as well. So I think so some of the wild ideas come from not rejecting ideas. But there's some people that don't have that many ideas to reject. Rejecting good ideas is very commonplace because it seems they're called impossible or expensive. People get confused about expensive today and expensive 2 years from now. And somehow the fact that it's expensive today stops us dead in our tracks. But the generation of ideas, I think once you had the part of its history, it's a little hard to recreate. But once you get a certain number of successes with crazy ideas, then it encourages you and everybody around you to do more of them. And so it's a autocatalytic loop.
Did you have any idols or inspirations that you looked up to?
Idols. Well, I certainly enjoyed my mentors, some of whom were distinguished in their hands-off approach. And I thought that was quite remarkable how much they could do with so little. So, for example, my math teacher in 9th and 11th grade, one of the people I dedicated my thesis to, basically told me to stop coming to class. And he gave me a book to read. And that was enough. That inspired me. And my 10th grade photography teacher kind of inspired me into a lifetime of imaging by giving me a 35 millimeter camera and say, go do something with it. And so people can make key just by singling you out for even a moment. So I think there's some mentoring that goes on there. And I was also quite inspired by Abraham Lincoln, not the original Abraham Lincoln, but a animatronic version of Abraham Lincoln.
I didn't know of the second one.
When I was 10 years old, I said, this is how computers should be. They shouldn't be this stainless steel beige thing. They should actually, look and talk like a human being. And I would say that we had better technology in 1964 than we have in 2020 in that regard. Better at least for impressing a 10-year-old.
Got it. One more question.
Now we have these kind of shiny robot dogs that don't even look like dogs. You know?
Oh, but I love them.
Okay. Be my guest.
What are some of the challenge and failure you faced that helped you shape who you are?
Well, it's a little hard to say because we didn't do the control experiment, you know, with one father or not flunking out of grad school. Or
very typical scientist thought.
I had to repeat ninth grade. That was, you know, most of these things. Oh, I lost my major source of funding just before I came up for tenure, which is one of the main things they evaluate, you know, your self-sufficiency. So these were major road bumps, but I just never had enough sense to really react negatively to these things or to the criticisms. You know, I always tried to see the half full part of the whole situation, or the fully full glass where it has air and water filling it. But yeah, I would say that almost all these setbacks helped in a certain sense. I think if you have too many successes, while you're while you're young, there's a large fraction of people get into this set where they don't want to disappoint. They feel that they have to keep up their reputation. And since my reputation was one of failure, I felt like there's only one way to go, which is up. And so I should change a lot of things, right? Well, if you're nearly perfect, you don't want to change anything, right? And so I think it actually can backfire, just like you can have too much or too little wealth. You know, if you have too much, then you spend a lot of time getting more or protecting it, or, you know, trying to spend it. While if you have just the right amount, then you're constantly trying to reduce the costs for yourself and for others, and other benefits. The frugality becomes this mother of invention.
Well, thank you, Dr. Church, for joining us today. It was a truly inspiring conversation to get to know you and your thought process, and of course, the Factor 10 vision.
Absolutely. It's been a pleasure speaking with you, Dr. Church. Thank you very much for doing this today. Thank you, everyone, for listening to another episode of Science Rehashed. Thank you to Dr. Rudy Tenzi for providing us with the music for our intro. You can find us on Facebook, Instagram, or Twitter. You can also visit our website at sciencerehash.com.
We would also like to thank all the members of Science Rehashed who contributed their time in making Science Rehashed possible. This includes our writers, Madura Lolikar and Kara Brenner, our marketing director, Carla Diavanzo, our sound editors, Tavi Pollard, Jared Warsaw, and Sophia Nastri, our assistant, Rebecca Solison, our creative director, Emma Brand, our producer, Shuang Zhang, and our business development director, Vici Lo. Our show is available on Apple Podcasts, Spotify, and Google Podcasts. Please subscribe and recommend our podcast to your friends, and send us your comments and feedback. Thanks for listening.